So welcome to today's session of the Discrete Maths 2 course. Thank you very much to those of you who are here in the lecture room to work with me on the topic for today's lecture, which is going to be the connection between regular languages and regular expressions. And as we will see, the connection is much deeper than just sharing the adjective regular at the front of language or expression. While people stream in, as usual, let's start by warming up, by getting our neurons buzzing by solving a little exercise. Hoping that the writing software will cooperate a little bit more with us today than it did last time around. So Dr. X was asking for you to come up with an NFA and make it as small as possible that accepts this language here. Okay, so this is the union of two languages. The first language consists of all the strings that only consist of A, possibly none. The second language consists of strings that only consist of B, possibly none, in a sequence. So let's produce an NFA that accepts this language. And let's make it as small as possible. Of course, if you're at home watching this lecture recording live or dead, or sorry, not live, you should stop now and do it yourself. I have the benefit of having a few people here who can help me. So here's the start state. My first question to you is, should the start state be an accept state, a final state, or not? One of your colleagues is saying yes, and that's right. Why?
Because it can be any non-negative amount of A's or B and or B's.
Okay, another colleague is saying, well, because there can be any number of A's or B's, so this any number can be 0. If you write 0 A's, you write the empty string. There is only one way in which you can accept the empty string in an automaton, at least according to the way that we've defined them in this course, and according to the way that Rosen defines them, namely the accept state. So the start state should be an accept state. Because by reading nothing, you can go nowhere. So you stay where you are. Okay, so what next? Okay, what if an A comes along? Now you read your first letter in your input string and it's an A. Okay, one of your colleagues is saying loop. Do you think this is a good idea? Okay, so if some of your other colleagues are saying no. And why not? Because if you read an A first, what is it that you want to remember? I mean, you want to go to a state that somehow carries the information that after you've seen an A, you only want to see what? Do you think you want to see a B after an A? You see, if a string starts with an A, then it belongs to the first language here in the union. So everything that follows the A's must be an A. Otherwise, it's not in the language. If we looped here, then somehow we will accept strings that do not have this pattern, A's only or B's only. Yeah. So absolutely. So well, that's a union. So the question is, I thought it was and and not or, but I mean, if it was an intersection, then this would be the empty set. Well, actually, the set that only contains the empty string. Sorry. So it's a union. Oh, that's important, actually. Yeah, this is union. Discrete mass 1 or even earlier. So that's union. So this is actually or. See, either you only have a string that only contains A's, or you have a string that only contains B's. Question? Yeah, I thought you were raising. Okay, okay. Thank you. So I read your mind. Sort of. Yeah, I can claim that for once I managed to read somebody's mind. Okay, so if we see an A, we go to a new state. And what kind of state is this? Is this an accept state or not? It should be an accept state. Why? Because a single A is a string that we want to accept. And now if in the state that we have reached, okay, so we are in the state here that we have reached, what kind of letters do we want to read? Only A's. And now it's a good idea to loop, because we can read as many as we want. Okay, the question is, what if we get a B? Remember, that's a good question. Remember, I told you, let's build an NFA, a non-deterministic finite automaton. If we get a B, we just cannot process this, the computation crashes, we cannot read our input string to completion, so we can never accept it. That's a big difference between a DFA and an NFA. In an NFA, in every state, you must have an outgoing transition labeled with every possible letter in the input alphabet. That's the reason why a DFA will always be able to read any input string that you feed it with to completion. And at that point, the only thing that matters is whether the state that you land in is an accept state or not. In an NFA, we may have states for which there is no outgoing transition labeled with some letter from the alphabet. In particular, from this state here, there is no outgoing B transition. So if you're in that state and you read B as your next input symbol, the computation of the NFA cannot progress, so it crashes. But since you must read all of your input before you decide whether you accept it or not, well, you cannot accept an input if you crash along the way while reading it. That's important. Okay, so what else? Yeah, we have to deal with B inputs somewhere. Where do we do it? Okay, but from where? So we want to have some B labeled transitions, but from where? We've already said from the initial state. Because initially, we might start reading a B, not an A. And if we read a B, where do we go? We go to an accepting state. Do we go to one that we already have or a new one? We go to a new one. Why? Because we want to remember that from that state, we only want to see B's, no A's. And you would have a B loop there. That's an NFA, yes, important, very important. So this is an NFA.
So you're saying that the difference between the NFA and the other one?
The DFA, yeah.
Is that in NFA you don't have to say what happens if you get to the next.
Okay, so the question is, am I saying that the difference between an NFA and a DFA is that you don't have to have outgoing transitions from a state for all possible input symbols? That's one difference, but there are more. So for instance, I might just as well construct a slightly different NFA here. Let me add one part of this automaton, and I make it blue. If I add the blue part to this automaton, would the accepted language change? Would this automaton accept the same language as the black part accepts? Or not? Okay, so your colleague is saying, doesn't the NFA always look for the accept state? Well, in order to answer my question, and in order to answer the question from your colleague, you have to remember what it takes for an NFA to accept an input string. Remember, for a DFA, since the DFA is completely deterministic, you feed it with an input string. There is only one way in which the DFA can process that input string. So after you read the whole input string, there is exactly one state where you end your computation. You look at the sex of that state. If it's an accept state, you accept your input. If it's not an accept state, you don't accept it. But in an NFA, you may have non-determinism. That's what the N stands for. This means, for instance, that if you are in your start state, in the initial state, and you see an A, the automaton could process it by either going the blue way or the black way. Now, if the whole input string is A, going the blue way would be bad, because afterwards you will not be in an accept state. Going the black way is good, because afterwards, at the end of having read the A, you would be in an accept state. Does it matter? No, because the mantra is an NFA accepts an input string if and only if it has some way of processing it that leads to an accept state. Remember my theater about the oracle? Okay, so you read an A in your initial state, you ask the oracle, which way should I go? And the oracle would say, use the black A label transition, not the blue one. Or in other words, if you want to be systematic, you just construct the tree of all the possible computations, and you will see that one of the branches of this tree that reads the A symbol leads to an accept state, and that's enough. If there is one way of doing it right, you will accept. Okay, that's an important point, and thanks for asking. That's a major difference between NFAs and DFAs. And by drawing the blue transition here, I've highlighted another difference between NFAs and DFAs. For each input symbol, you may have more than one outgoing transition labeled with an input symbol from any given state. In fact, any number, any finite number of transitions. And this any number could be 0. Yes? Okay, the question is, can you tell me again why the automaton accepts the empty string? Because the empty string is 0 A's in a row, as well as 0 B's in a row. Another question, yes?
After you choose A or B, can you choose a B after you choose A and go into error state by that?
Okay, so the question is, well, after you have, say, read the first A, can you afterwards read the B? Well, in this automaton, no, because after you read the A, so sort of if this is state S0, this is state S1, you read the first A, you go to state S1, and now suppose that you want to read a B. The next input symbol is a B, you can't. There is no outgoing A label, a B label transition from state S1. So you cannot actually read your all input, the computation crashes. You could, of course, add the B label transition going to an error state, but then you basically would be building a DFA. You're not using the power of non-determinism at all. Absolutely. Every DFA is also an NFA, typically bigger than you need. So the message is, when you attempt the exercises on NFAs in the Automata Tutor, try to make use of non-determinism. Try to make them as small as possible, because the Automata Tutor will not give you 10 if you're not using non-determinism. It will give you 8, that's correct, but perhaps you can remove something. That's because the goal of the exercise is to learn about non-determinism. If you're using determinism all along, then we could just as well not introduce non-determinism. And today you will see also some other good uses of non-determinism to simplify constructions. Lots of questions. Ladies first, if you don't mind. Mm-hmm. Okay, that's a good question. Sorry. Sort of in the Automata Tutor, sometimes you will see these epsilon things. Okay, ignore them. Ignore them, because automata sometimes actually a more useful definition of NFA would have something which is called epsilon transitions, which unfortunately Rosen does not use. And today I will give you an example of how you can get into trouble when you don't use them. But since Rosen does not use them, we are not going to use them in the course. For some of the exercises, I actually disable them. For some other ones, I forgot to do so. That's why you see these epsilons. But ignore them. Ignore them. Only use the A and the B. Thank you. Excellent question. Okay, so the question is, can I do an example on the Automata Tutor for NFAs? Yeah, the answer is yes, I can, but I need to... Oh, well, okay, just a second. Just a second. The answer is yes, if I could get access to the Automata Tutor. It depends on... if you haven't followed the discussion yesterday, it really depends at RU, it really depends on how I'm connected. Well, yes, it's working. I sent a message today, perhaps they fixed it. So yesterday there were some very interesting things happening here. So let's go to the practice problem sets. And let's go to, okay, contains AAA, NFA. Shall we do that? Solve. Okay, so there you are. When you are in a state, you see this thing. We ignore this epsilon thingy here, as I said, so that we only focus on A and B. And we want to build an NFA that accepts all the strings of A's and B's that contain AAA in them. Okay, so what do we do? Okay, we try to use the power of non-determinism. So if the string contains AAA somewhere in it, well, it will start with some string of A's and B's. And then all of a sudden we guess that we are meeting the start of the AAA pattern. At that point, we want to come down 3 A's, after which anything goes. Let's see. So first of all, how do we express at the beginning, before I see the AAA, I don't care what I see. You loop on A's and B's. Okay, so how do you produce the loop? Okay, for the DFA, the loops were given to you. Now we got to draw them, actually being not particularly... so I was trying to play with this the first time overnight, and I was getting cramps trying to get these loops. But the best way to get them is you take the A, say you want the A loop, you push this, and then you push it back, and you get the A loop. It took me several centuries to figure that out, so I'm giving you the short story. I was trying to draw loops myself, and I was getting cramps on my wrists. We do the same with the B loop, up and down. Then we get the loop. Okay? Well, we don't want to be in this loop forever because we want to check for AAA, 3 A's in a row. So what is it that we do? Well, at some point, we guess that the A transition, the A symbol that we read is the start of the pattern AAA. Okay, now we got to change state. Why? Because we want now 2 more A's. So that's why we create 2 more states. If we see an A, we go here. And actually, since I guessed that this is the start of 3 A's in a row, from state 1, I don't want to see anything else but A's. That's why I don't add B transitions. Actually, I didn't try this before, so I'm curious to see what mark we're going to get. Now, what about state 3? What kind of state is this? It's an accept state, so we make it final. Okay, the question is, wouldn't this accept some strings that would contain A, 2 B's, and then 3 A's? But those are okay. So the string must contain AAA's, 3 A's in a row somewhere. It doesn't have to be at the beginning. It doesn't have to be anywhere. It could be anywhere. So if you have a string that has 3 A's in a row, well, before the 3 A's in a row, you can have anything. And after the 3 A's in a row, you can have anything too. So we are not quite done yet. Because from state 3, what is it that we want? We want to loop. And then I take the question. Okay, so again, I've read your mind. Fantastic. We are on the same wavelength today. Okay, shall we see what happens? Are you happy with this? Well, actually, you should never see what happens. You should first think, before you press the submit button, you should think. Now, for me, it's very difficult to think, but you can think for me right now. So I'm lucky. I have, let's say, 40 processors in front of me who are working in parallel right now. And this is much better than one processor, namely mine. That's also running Ubuntu version 2 rather than 14.10. 2 questions. Okay, so the question is, shouldn't number 2 be an accept state? And the reasoning is, what if I see an A, I loop, and then I see 2 A's? Well, that's a good question. However, remember that an NFA accepts if it has one way of processing the input string that leads to an accept state. So if we made this, so this means in particular that instead of looping on the first A, the automaton would just go this way. Would it also be dangerous to mark 2 as an accept state? Some people are saying, yes, it would be dangerous. Why? Because we could get the B first and then AA, and you would accept BAA. Symbol at the time, yeah. Okay, so the question is the DFA reading one symbol at a time and the NFA is reading the whole string? Well, no, they both read one symbol at a time. It's just that the acceptance condition is different. In a DFA, yeah, okay, the question is, how can the NFA know which is the right way of, okay? The fact is that it doesn't. It doesn't really. So you can think it 2 ways. One of them is, okay, the NFA magically chooses a right way of processing the input string if one exists. This corresponds to the condition there is some way of processing your string that will lead you to a happy state. The other one, which is the more prosaic one, and it's the one that really you would do if you were actually implementing this stuff is you try all possibilities. You have a tree of computation starting from your start state, like we were drawing last time round. And if somewhere in this tree you reach a state which from the initial state that you reach by reading the whole input and that lands in an accept state, then you're happy. In other words, like with the Pokemons, you try them all. Collect them all. You collect all the possible computations. If one of them works, you're happy. Okay, so are we happy to press the submit button? Anyway, sort of, I'm just losing my face. Well, yeah, there you are. Not only we accept the correct language, but we get 10 out of 10 because it's not possible to do better or anything substantially better than this. Question?
Would you get a 10 out of 10 if the string should also be of even length?
Okay.
You have to go odd numbers in the first state.
Okay, so the question is, would you get the 10 out of 10 if the string should also be of even length? Well, let me give you two answers. First of all, certainly not, because this would be contradictory into accepting. Okay, so you're saying all strings of even length that have a somewhere in them. Then this automaton would not work. You would have to modify it. So it would not accept that language. So this accepts, for instance, a, which has the right pattern, but is of odd length. Lots of other strings which accept the right pattern that are. So the automata would be more complicated in this case. In the question that you have on the automata tutor, it would be as simple as this one. But the other interesting part about this question is, to answer it, I would have to know the precise algorithm that the automata tutor uses to mark the NFA assignments, and this hasn't been published yet. So what I'm telling you is the hints that I received from the automata tutor guys who actually know how the grading takes place. But like with the DFAs, the grading is a combination of at least, I think, 3 different notions of distance between the best possible solution that uses non-determinism and the one that you come up with. So it's, but they haven't published the algorithm yet. So the grading algorithm. So the details, I don't know. Any more questions? Well, we are using a lot of the lecture on this, but I think it's for a good cause. Or at least I hope so. Could I implement, then we would have to do it on paper, all the strings of even length. Do you mind if I give it to you as an exercise and you can discuss it on Piazza? No, I mean, it's not that I don't want to do it now. It's just that otherwise we don't do what we were supposed to do today at all. And even if I don't mind sort of going slow, then at some point sort of I need to cut. But yeah, that's a good question. So exercise for everyone, and we discuss it on Piazza, or we can do it in the break. All strings of even length that contain the pattern 3 A's in a row. So we can also do it during the break, assuming some of you have not done it instead of listening to me now. Okay, so let me summarize what we've seen so far. We've seen, as a chef at Dill restaurant could put it, we've seen regular languages 3 ways. We've seen them smoked, we've seen them salted, and we've seen them in Misa. Yuck. Accepted by regular languages are those accepted by DFAs, those accepted by NFAs, and those generated by regular grammars. So if someone asks you, here's a language, is it regular? Well, to convince that person that the language is regular, you can either show her a DFA that accepts that language, or an NFA that accepts that language, or a regular grammar that generates that language. There would be 3 different ways of actually showing the same thing. The question that we are going to address in the remainder of today's lecture is whether we can actually characterize syntactically the patterns that finite automata can check. For instance, my string will have 3 A's in a row. We built an NFA that checked for the presence of that pattern in an input string just before. So that is a pattern that finite automata can check. But can we characterize once and for all of the patterns that finite automata can check, so that we know what language we can use to express dot patterns? And of course, the answer is yes, because otherwise the lecture will be over. And we could go back and work on the question that your colleague here in the first row was asking before. So what are these patterns? Well, there's something that you already know and love, namely regular expressions. Regular expressions are a language for describing the patterns that finite automata can check. Now, before we introduce regular expressions, we need to look at a couple of operations that you can perform on languages, because they correspond very closely to some of the constructs, the constructions that you have over regular expressions. Now, languages are nothing but sets of strings. So as you've seen, you can union languages together, you can intersect languages together, and in fact, if you really want, you can do any set theoretic operation over languages because they are sets. But life would be pretty boring if those were the only things that we could do with languages. With languages, we can do things that are specific to the interpretation of languages as sets of strings. One of the things that we can do is to form the concatenation of 2 languages, which is denoted by this dot here. If somebody gives you 2 languages, capital A and capital B, you can use them to form a 3rd language, which is A concatenated with B. Now, what are the strings in this language? They are all of the strings that you can form, that you can construct by taking some string U in the language capital A, some string V in the language capital B, and concatenate them together. You do this in all possible ways, and out comes the set of all strings that are in the language A concatenated with B. Example. You were screaming for it, I'm sure. Okay, so let's assume that A is a language that contains the strings A and AB, and capital B is a language that contains the string B and BA. What is A concatenated with B? Well, that's a language, so it's a set of strings. But what strings are they? Well, remember the algorithm. It's the set that contains all of the strings that you can form by taking some string in capital A, some string in capital B, and concatenating them together. Okay, so what are these strings? Okay, so okay, the question is, I'm having a hard time understanding what concatenating 2 strings mean. Okay, the answer is, you take the first string, you write down all the symbols in it, and afterwards you write all the symbols in the string, in the other string. That's what concatenation is all about. It's like really like list concatenation, but over strings. You first write all the things in U, and then all the things in B, and you get the string U followed by B. But I hope that the example will clarify this. So for instance, I can take the A from the first language, and the B from the second language. I write A and then B, and I get AB, AB. Well, I could also take A from the first language and BA from the second language. What do I get out of it? ABA, ABA. Okay, I could take AB from the first language and B from the second language. And I get ABB. Or I could take AB from the first language and BA from the second language. And I get ABBA. Waterloo, we are done. Or whatever other song you prefer. Huh? Okay? So, question. Okay, the question is, you don't do it with the other way around. That's an excellent question. If I did it the other way around, I would be creating the language B concatenated with A, which in general is a completely different language. Why? Because concatenation, even though we write it with a dot, is not commutative like multiplication. If I write Luca first and then Sigridur, I get Luca Sigridur. If instead I write Sigridur first and then Luca, I get Sigridur Luca. And the two names are different. String concatenation is not commutative. With apologies to Sigridurs in the audience, here, both here and at home. Okay? But excellent question. So let me ask you this question here now. Suppose that I take my language A and I concatenate it with the language that only contains the empty string lambda. What do I get? A, as your colleagues here are saying. Why is that? Well, because the concatenation of the two languages are all of the strings, is the set that consists of all of the strings that you take by taking some string in the set capital A and then writing nothing after it. But if you write nothing after it, you just have the same string you started from, which is in A anyway. So you get exactly A. And in this case, you actually have that I could do it the other way around. Because if I write nothing before or after a string in A, it doesn't really matter. I add nothing to it, no matter whether I do it before or after. I do nothing, then I write my name. It's the same as I write my name and then I do nothing. I've only written my name. Okay, just to make sure that we understand this concept. And I mean, by the way, if you get bored, if I'm sort of rehashing the obvious, scream, so that also the people somewhere at home who are listening to us now can hear you. So in that case, we go faster. But just to make sure that we understand what we are talking about, let's consider a pathological case. What is the language that results by concatenating a language A and the empty language, the language with no strings in it? Okay, so one of your colleagues said A. Let me call this guess 1. Is there any other guess? Or sort of guess is not derogatory here. Is there any other suggestion? I should have read. Another colleague of yours is saying empty language, which I like more than the first suggestion. Why? Why? So let's think about it. Okay, A concatenated with the empty language is by definition what? It's the collection of all of the strings that you can build by doing the following two steps. Take a language from A. So take a string from A, U. Take a string from the empty set, V. Concatenate them together. Houston, we have a problem. How many strings can you build this way? Take some string from A. That might be okay. But the second step says, take some string from the empty set. There's nothing in the empty set. I cannot do that. So can you ever build any string in the concatenation? No, because you cannot actually pick any string from the empty set. So you cannot build any string in A concatenated with the empty language, which means that you've generated the empty language, a language with no strings in it.
Can you think of this all then as null?
Oh, the question is, can you think of this Norwegian as the null? Well, so in fact, if you implement the data type of sets, that would be a representation of the empty set. It would be like an empty list, a list with no elements. Yeah, the concatenation in C would crash, I guess. Yeah. Okay. Fantastic. But you can actually concatenate an empty list with something else. So you have to be a little bit careful of. So in general, in fact, in the abstract data type of sets, you don't have a concatenation operator, because you're not meant to concatenate arbitrary sets. It only makes sense when these are sets of strings. Okay, excellent. So before we take a well-deserved break for you, not for me, let's look at the other operation that we have here. This one is called the Kleene star operation. Now, what is the Kleene star? Okay, well, if you take a language, A star, the Kleene star of the language A, consists of the set of strings that you can build as follows. Pick any number of strings from your language A and write them one after the other. The result will be a string in A star. Okay? Pick any number means pick 0 strings, for instance, from the language A. If you write 0 strings one after the other, what string do you get out? Do you write anything? No. So you've written the empty string. So the empty string is always in A star. Any number means, for instance, one string from A. So everything in A is also in A star. Any number means 2 strings, for instance, from A. So A concatenated with A is also included in A star. But it could mean take 3 strings from A, 4 strings from A, 154 strings from A, 1 billion strings from A, which could all be the same, and you write them one after the other, and you get a string in A star. Example. Suppose that my language A consists of only the string AB. What is in A star? That's going to be an infinite language now, not a finite one. Because any number means any number. 1, 2, 3, 4, 5, 6, 7, and I stop here. 0 as well. So what did we say before? There is a string which is always in A star. The empty string. I take 0 copies of AB and I write them, so I write nothing. Okay? Or I can take 1 copy of AB and I write it. Or I can take 2 copies of AB and I write them one after the other. Whoops. It's just that I get inspired by ABBA, things get strange. But I mean, ABAB. Or you can take 3 copies of the string and I write them. Or in general, I can take n copies of this string for any n and I write them. So in other words, this is AB to the n, where n can be any number. So that's what the cleaning star operation does. Okay, you might recall that we already have seen this star. So for instance, we said that the set of all strings is over AB is AB star. Now, does this match with our definition? Well, sure it does. It's the same thing. What I've said is that, well, first of all, this is a language. It's not just an alphabet. It's also a language. The language that consists of two strings, the string that only contains A and the string that only contains B. AB star, according to what we just said, should be the set of all strings that you can form by taking any number of A's and B's and writing them in whatever order you like, which is a way of forming any string of A's and B's. So the notation that we've used so far to describe the set of all strings over some alphabet is in complete agreement with what we just said. Oof, I know the cleaning star can be a tough nut to digest, especially before lunch or after lunch, depending on whether you've already had lunch. I haven't. So it's time for a break. After the break, we are going to work with cleaning star again, and we are going to see how these operations that we just introduced are at the core for the language of regular expressions. And in fact, I'm pretty sure you've seen commands like this before. But if you haven't, then you haven't been using Linux or Unix or Solaris or any proper operating system. Okay, and we'll see what this actually means and how it connects to cleaning star. Break.